Let's look at this queue implemented with lock-free, as implemented as a lock-free queue. Most things are similar, but all the details are much more complicated. So what is similar? What is similar is that we have a head, we have a tail, we have a node. Initially, this node has no useful data, and then we have, both point there, and this is the queue. Okay, and again, we add things to the end and remove things, the next one after what the head points to. Let's start looking at adding things to the queue. Okay, so let's say, what I will do now is to explain not exactly according to the source code, because the source code is quite complicated to start looking at. But I will give this situation when there is only one thread, and then we can accept easier that we just add as in the sequential, this single-threaded case. And then we will see what can happen that complicates things when we have multiple threads adding things to the end of this list. Okay, so let's just think that there is only one thread, and we imagine that we can see how this should be done without looking at the source code. So this should be the result. Okay, fine. Now we can consider which variables should be atomic. In the stack, it was only the top of the stack, the stack pointer, that should be atomic, since a thread can only add or remove things using the top of the stack. Here, it's quite clear that both the head and the tail should be atomic, since, well, if somebody wants to remove something from the queue, it clearly will modify the head, and this is similar for the tail. So these two must be atomic pointers, since multiple threads can want to modify them concurrently. Of course, only one of them will be able to modify it, but several can try to do it at the same time. So they must be atomic variables. Anything else that should be atomic? The key should not be atomic. We assume that once the key is in a node in this list, it is not modified. Okay, so maybe something else. Well, what happens if two threads want to add something to this one? They will both try to modify the next pointer. And therefore, not only the head, tail should be atomic, but also the next pointer. So let's look at the structure. Okay, well, first of all, I should say that this queue that we will look at, that we are looking at, it was invented by Major Michael and Michael Scott at the University of Rochester, and it was published 1996. So the types, again, we have the pointer, and it contains a node and a serial number to avoid the ABA problem. And we say type def atomic pointer to add this atomic to the type. To this pointer type. Well, the pointer type is a struct, but it contains a pointer. And then the node should have an atomic pointer, and the queue should have a tail and head as atomic pointers as well. Okay. What can more happen? Say now that we have one thread, T1. It wants to add a node with value 4, for instance. So what does it do? Or actually, what should it do? What are the operations? As in this sequential case, it should change the next pointer of the last node, and it should update the tail to be there. But let's say that is not what happens. When this node comes here, it is able to add this pointer. But now it experiences something which makes it wait. For instance, a cache miss, or anything that delays this thread. What can we do then? Well, we don't want to wait. The parallel data structure is still in use, and now comes another thread that wants to add something. And what does it do? Well, clearly it will load this pointer, and it will load the next pointer of this. Okay, so we can say that T2, that's the tail, that's a copy of the tail for thread 2. So as expected, it reads the queue.tail or arrow tail. And what should it do then? Well, it should what it will do is to discover that the next field of this node is not null. Okay, so it has just discovered that thread 1 went to sleep, or well, maybe not sleep, but just waiting for something, and did not finish what it should do. And this is nothing strange. It could be any of the items that I listed or that may delay a thread. It could be a cache miss, anything, or just preempted. Okay, so what we want to realize is that a thread may discover that the tail is not the correct value. Okay, so what should it do? Should it insert 5 here? Well, and forget this one. Not so good. Let's forget that idea. But what it can do is to update this one to the next field of the tail that it read. Okay, so what it can do is to set this pointer to number 4. Okay, and then what should thread 2 do now? It should start over. Okay, so it does, and what happens then? It will see that tail. Now the value of the tail has gone here. It's here now, and so this is the tail for thread 2. Actually, we can keep this tail for thread 1 because it's still there. Okay, so now thread 2 wants to add the 5 to this one, and what can happen then? for instance, thread 2 can fall asleep and some other node comes in and does something instead. Okay, let's say it does. So now we have thread 3. Thread 3 wants to add another node. Okay, and what does it do? It reads the value of the tail, and it sees it's a node with value 4. So now that one is there. Okay, and then it updates this pointer atomically, of course. Okay, and then it can also say it doesn't fall asleep, so it also updates this pointer to, no, that was not what should be done. It updates this one to this one. Okay, and let's say now that these two threads wake up, and what they want to do is to update, well, they both could insert their nodes. So now they want to update the queue tail. Okay, and that is not a good thing to do, because they have no clue about that it's already been fixed. Okay, so what has to be done for this one to not set queue.tail to let me see, it inserted 4, so it should not set this pointer to this node. Well, what it has to do is to check if the current value of queue.tail is equal to the value that it thought it was. So if, basically it will be like this, but atomically. If queue tail equals T1, that's the value of tail that thread 1 saw, then queue tail equals, I just say 4, that node. Okay, and that should be done atomically, which is, how to do it atomically. It's with the atomic compare exchange function. So, it was much simpler in the stack, and now what happens is that several threads can have added things, and the tail pointer of the queue has it's not up to date, but it can be moved forward, and eventually it will be pointing to the last node in the list. So okay, so what the threads can do is to, if they succeed, to add their own node to the end of the list. It's not certain that they succeed, and if they do not succeed, they have to restart. Okay, and then when they have added this node to the list, it's not certain that it is they who should and can update the tail pointer of the queue. Okay, because they may have fallen asleep, got a cache miss, and somebody else may have updated the tail. Okay, recall, when you modify an atomic variable with atomic, not always, but if you use, okay, it should not be written like that, but that was the non-atomic meaning of this comparison. But when we use atomic compare exchange, we should ask the question, is it we who have the new value of this atomic variable? Okay, so typically we have made a copy of the tail, and then we can and we have also, so we have a copy of the tail of QT, and we call that copy, we call it tail I for thread I. And then we also have a next variable, and if in the atomic compare exchange, if this value that we can, this is an atomic and we can compare it atomically with this one, this is not atomic, it's a copy of this one that was valid just when we returned from reading this one. But if they are still the same, then we set QT to this one. And if it's not, well, then we try again. I mean, start over. Okay, so in summary, from this figure, what we can say is that we try to add our node to the end of the list. That may or may not work. And okay, when does it not work? Okay, we can take that example as well. So say now that we have 2 more threads, T4 and T5. Okay, and they want to add 11 and 13. Okay, and both of them read their copy of tail. So we have T4 and we have T5. Both use this node as both thread 4 and thread 5 think 7 is the last node in the list, which it is. Okay, and then what do thread 4 and thread 5 try to do? Well, the next thing that they should do is to read the next value of this node. Okay, so they do that, and then each of them tries to add their node to this. And the one that is first succeeds. Okay, so let's say, well, we can put them here instead. Say that 11 was first. And what should thread 5 do to discover that its copy of tail is not up to date? Well, it can observe that the next field of this node is no longer a null pointer. And therefore it has to start over. But before starting over, it actually is very helpful and kind and nice. So it tries to move T to this one, as we saw previously for the other nodes. And then T5 will try to add 13 to this. But okay, so the last thing that T5 did, in case T4 did not already do it, is to update the tail to be, this one should go there instead. Okay, and then it starts over. Okay, it's not certain that it is T5 who did that, but it could be. And if T4 fell asleep and wakes up, and then it will discover that some other thread has already updated the Q tail to the newly inserted node. So it will not try to do it again. Okay, so let's next look at the source code.